Right, section 3.5 just has an activity as it's a summary of what we've done so far in chapter 3 of curve sketching. So here are the solution set activity. I've written most of them out already, otherwise this would take way longer than you're going to want to listen to me talk. So I walked you through here step by step how to follow the guidelines that we've seen to graph f of x equals x minus 1 over x squared. So first, find the domain of the function. This function is defined everywhere except at x equals 0. So negative infinity to 0, union 0 to infinity. Find the intercepts. Well, x equals 0 is not in the domain, so there's no y-intercept. And the x-intercept is going to occur when the numerator is equal to 0. So that's going to happen at x equals 1. And so that gives us a point on our graph. It gives us the point 1, 0. Okay, find asymptotes. Typically, this wouldn't be enough space to do this. It happens to be for this function. The vertical asymptote is going to occur when x is equal to 0 because it's not in the domain. It makes the denominator equal to 0. And then for horizontal asymptotes, we have to think about the limit as x approaches plus and minus infinity of x minus 1 over x squared. Well, those are two polynomials where the degree of the denominator is larger. So we saw in the previous section that that limit is going to be 0, which gives us a horizontal asymptote at the line y equals 0. Okay, now we want to find where this thing's increasing and decreasing. So we take its derivative. There it is. Using the quotient rule. And then I did some factoring and simplified that derivative a little bit. Now here is a spot where we do want to try to simplify the derivative because we know we're going to have to take the second derivative to think about concavity. So the simpler we can make the first derivative, the simpler our lives will be taking the second derivative. Okay, so we see that this has critical values of 0 from the denominator and 2 from the numerator. So we go ahead and set up our table here of intervals to determine where the derivative is positive or negative. We look at 2 minus x and x cubed because they are the pieces that make up the derivative. We can fill in that chart there and we see that f of x is decreasing from negative infinity to 0, increasing from 0 to 2, and then decreasing again from 2 to infinity. So that means we have a maximum when x is equal to 2 because we switch from increasing to decreasing, so we have a maximum at 2, 4. The chart here makes it look like there's a minimum at x equals 0, but we've learned above that x equals 0 is a vertical asymptote, or at least that the function isn't defined there. So there is no minimum at x equals 0, just a local maximum. All right, so I'm going to play the same game again now with the second derivative to find concavity. And so it looks like this. The second derivative, again, using the quotient rule, I simplified it a little bit. And we get critical numbers of 0 and 3. And so now our intervals are negative infinity to 0, 0 to 3, and 3 to infinity. Play the same game. We look at the two pieces. We decide if the second derivative is positive or negative. And we see that our function is concave down from negative infinity to 0 and 0 to 3, and then switches to concave up from 3 to infinity. So that gives us an inflection point at x equals 3. Which is the point 329. Okay, so we also need to know, let's see, I wanted us to sketch it, but before we can do that, we need to know what's happening around the asymptotes, or around that asymptote at 0, the vertical asymptote. So as x approaches 0 from the left, we're going to have negative things in the numerator and positive things in the denominator, but the denominator is approaching 0 while the numerator is approaching negative 1, and so this thing's going to approach negative infinity, and the same thing will actually happen from the right. So we can start sketching this graph. It looks like this, and like this is what we just learned from those two limits. Now this side, we learned we have an x-intercept here at 1, 0, a maximum at 2, and a change in concavity, an inflection point at 3. So we come up, we hit our maximum, we're still concave down. Then as we hit 3, it's going to be a little bit hard to see, but we change to concave up and we're approaching the x-axis in the long run. Over here, let's see, if we put negative 1 into this function, what do we get out? Let's go all the way back up. Negative 1 minus 1 is negative 2 over 1. So at negative 1, we're at negative 2. So that means we're here. And let me erase this mark. And I know I'm concave down, and I know I'm approaching the x-axis in the long run, and I know I'm approaching, the y-axis there, and I know I'm approaching the x-axis here. So there's a reasonable sketch of this function using the information we learned above. Okay, another example for you guys to walk through. The solutions are all here. Complete the steps above to graph x over x squared minus 4. So we find the domain, -2 and 2 are out of the domain. We find the intercepts, 0, 0, and 0, 0, the only intercepts. We look at the asymptotes, x equals -2, x equals 2. Look at the limit as x approaches plus or minus infinity. Again, it's going to be 0 in both directions. So there's our horizontal asymptote. So let's make a note of that. These are vertical. This is horizontal. Take the derivative using the quotient rule. Simplify it a little bit. It gives us the critical numbers of -2 and 2. Make our table. Our table looks like this: -infinity, -2, -2 to 2, and 2 to infinity. And this function is decreasing everywhere. So we have an everywhere decreasing function, which means we have no maximums or minimums. Okay, we battle through the second derivative and a little bit of algebra. Looks like this. The critical numbers are -2, 0, and 2. So now we have 4 intervals, and our function is changing concavity. So we make our table here, and we see that we get an inflection point at 0, 0. But it's changing concavity at -2 and 2, but those are vertical asymptotes. So we see that the concavity changes, but no inflection points. And then again, we should think about the behavior near those asymptotes. And we see that as we approach -2 from the right, we're approaching infinity. -2 from the left, negative infinity. 2 from the right, infinity. And 2 from the left, negative infinity. Okay, so we can put all of this together and go back up to the graph. So this thing is always decreasing. So it looks like this. We know it's approaching 0 in the long run and coming down towards negative infinity here at -2. And then it crosses the x-axis at 0, 0. It's always decreasing. Changes concavity here from concave up to concave down at 0, 0. So there's a concavity change right here. This is an inflection point. And then it's always concave up on this last interval. It's approaching x equals 2 and y equals 0 as the asymptotes. And so there's a reasonable sketch of that graph using all the information there. So hopefully that the solutions are all laid out there for you. I'll scroll through them one more time here slowly, and you can pause the video to see certain parts of them if you want to check your work. So here's all the work with the first derivative. Here's all the work with the second derivative. And then here's the table for concavity. And then finally, what we learned from that. Here it is. And lastly, we need to know about what's happening near those vertical asymptotes. Behavior near vertical asymptotes. Okay, so hopefully you can pause the video where needed and go through and check your solutions to this activity, and then dive into the problems that are assigned in the textbook here in 3.5. As you can see, this graphing takes patience. It takes time and walking through it step by step, but try to tackle the few problems that are assigned.